Hello, and welcome to what may be the final episode of this Prime Civ live proving adventure, right? So, um, let's see. Since last we spoke, which was 2 days ago my time, I drew this little picture with the help of ChatGPT and Mathematica. This actually is what a rake is. So I thought I've been trying to draw a picture of it. And I haven't had a good visualization yet. I'm not very good at Mathematica yet, but I am. I drew this little picture, so you can see this is a rake that has the slope of 6. This skewed, so like it's squished down quite a bit. And we're starting at 0. We have the numbers. We have the line 3 plus 6n, 5 plus 6n, and 7 plus 6n. So these are the 3 numbers that you get after in this prime civ, or the 3 lines that you get in this prime civ after you factor out the multiples of 2. And so what this is telling us is that 3 is the next prime that we've encountered, and we're about to scratch that out. And that will leave us with these 2 lines, 5 and 7, which is where all the like everything on this line right here. 3 is a multiple of 3, and 6 is a multiple of 3. So every number on this green line, which would be 3, 6, 9, and whatnot, is a multiple of 3. Or I guess not. I guess it would be 3, 9, and we've already scratched out the multiples of 2. So it's all the odd multiples of 3 are on that line. And because they're multiples of 3, none of them are prime. But these 2 have all the primes in them. All the other primes are on these 2 lines right here, going off into infinity. And then what we're going to do is we're going to scratch off the 3. That's the prime civ step is you identify the smallest prime. You remove all the multiples of 3. Well, they're all conveniently on this line, so all we have to do is remove this sequence from the rake, right? So we just trim that little third line there, and then we've got these 2 numbers, and what we're going to do is we're going to say, okay, well, 5 is the next prime, and so we multiply the so in order to distribute that, I guess, or to well, just the next step in this algorithm, which is not efficient, but it's what it does, is it takes the number 5 that we find. So I guess 3 is already a factor of 6, so now we need a number that is a multiple of 5 as well as this. So we have to multiply 5 times 6, and we get 30, and that's going to be our new slope. So it's even further tilted upwards, which gives you an idea of how fast this number, these numbers grow. And we're going to multiply 6 by all of these, and then we're going to take each one of these dots, basically the first 5 of them, because we're multiplying on the number 5. So me talking to ChatGPT about how to make this plot in the Wolfram language. And after I do 5, it's going to take all these numbers that are here, and each one of them minus the 3, right? Each one of them on the top 2 lines is going to be the base of a new sequence, right? And then, we'll have the number 5 plus 30n, and then we'll have 25 plus 30n from the after we do this. Basically, each one of them is going to lead to one of the there's 5 numbers here, 1, 2, 3, 4, 5 in each column. So one of these numbers has to be divisible by 5, basically, and it happens to be 5 and I guess, right? So it'd be 25 would be this one right here. So 6n times 3 is 18 plus 7 is 25. Okay, so we take these dots, and now we have all these numbers, and then we scratch out the ones that would be here. I've already done it. I removed the line that said 5 and removed the line that said 25, and so it just you wind up after the the step, you wind up with like they're not evenly spaced. Here they're evenly two apart, but here they're kind of like spaced a little bit differently apart. And you can also see that if we take them in sequence, which is what the algorithm currently does, then for the first however many terms you have, however many sequences you have, we're going to go up this line, and we're going to say basically read off the numbers 7, 11, 13, 17, 19, 23, 29, 31. And then the next term is not, it's not completely ascending, right? It comes up and then it zigzags back down because, like, we can see that we're over here. This is probably this would be 1 times 7, so this would be the number 37 right here. Okay. And I guess that would be 39 and so on. 37 and 41, I guess. 39 would not be prime; it would be a multiple of 13, right? Anyway, so this is what a rake is. This is kind of the algorithm that I'm trying to prove. This is not my invention. I guess my take on it was to use arithmetic sequences, but somebody else invented the algorithm. Daniel Torres, I don't know if he watches this. So hi, Daniel. Anyway, so that's the start on a visualization. I'd really like to see, it's like to animate all this stuff, but that's a problem for the next couple of weeks. All right, so where am I at right now? I have repaired some of the damage and then created some new damage. So right now I'm down to one function. So the thing I was trying to prove in my last video, I spent 5 hours on it, or 4 hours on it, didn't get anywhere, or got somewhere, but didn't prove the thing I wanted to prove. But basically that after this partitioning step, when you go from so removing the line was on my to-do list, right? Like on all of it's implemented, but proving that removing this third line or the bottom line is safe, that was on my to-do list. It's now done. But the partition step is the step from going from these 2 lines to the 10 lines, and then now there are 8 left, right? And then the removing, it goes first you sort the lines because again they're zigzaggy, right? So you want to take all the or I guess actually rather first you take the these 2 lines, you partition them into 10 lines by multiplying by 5 and creating five new lines each. You sort them so these things are ascending because again, like once you do this, you're going to have, after the next partitioning step, you're going to have all these numbers in there, and plus more off to the side here, and they're going to be out of order. So you sort them, and you get just ascending lines going off like this, and then the third step is to remove the ones that are multiples of of the prime that you just discovered. So those are the steps of a prime set, right? And of course that leads to a massive blow up in the number of lines. You calculate the terms on the fly, but just the number of lines grows. It goes, you multiply by 7, then 11, then 13, and 17, and so on. So it just expands very, very quickly. But the idea is that the proof that I was working on last time was the proof that when you do this step, every number that was on the lines that were, the lines that were still there after crossing off or cutting the lines, that every number that was projected, that was generated by them, is still generated by this new collection of lines. That's the step that we need, and so that I have not proved yet, and that is the one remaining step that I need to prove for rake. I call this thing a rake. And basically I'm throwing away the proof attempt that I did in the last stream because it was all based on natural numbers and division on natural numbers, and I don't feel confident that I can get there. Meanwhile, I've got like a bunch of things I've already created that attack the problem from a different way, and I think that I should be able to solve that. I kind of talked about that a little bit. I'm going to work on that tonight. But In the meantime, I also I took a break from that, and while off camera for the past day or two, I proved all of the steps, all of the 3 theorems that I needed about that these numbers that the set of numbers represented by these 2 lines is the same set of numbers represented by, and now I can't scroll, by the one below it. Chrome just froze up. There we go. With the minus the 2 lines that I scratched out. So that's what. Oh, actually, I guess the proof was about the scratching out step. So the proof is about the rem drop, rem keep, and rem same. So the idea is that if so I'm gonna call the function with the rem means remove. So remove all the multiples of some number j. So I'm going to say rem 5, right? So remove all the multiples of 5. And what it does, in order to do that, well, okay, right now the multiples of 5 are scattered across both of these 2 lines. So that's why it does the partition step. And now it comes up with lines, and it has a line here that is starting with the number 5, and it's 5 plus 30n. And that would be, again, 5 and 30 both are divisible by 5. So every number on that line is going to be a multiple of 5. And then also, when you multiply 7 and you add, you partition that, one of the lines gives you 25 plus 30, and both of those are multiples of 5. And so that line also has nothing but multiples of 5. And so that the idea is that, okay, the rem operation drops only those lines, only those numbers. So I had to prove that. Then I had to prove that it keeps all the other numbers, right? Any other number that was in here gets kept. And then the tricky one is that we have to show that that it didn't add any new numbers in, right? So that was tricky. And the tricky part is it's not true. Because or it's theoretically not true. It's true in this case, but it's not true for the general case, because I have a problem, right? And the problem is, well, let's show the code. The problem is that if so rake is just a general purpose data structure. It's not specific to a prime sieve. I mean, that's what it's intended for, but you can use it for other, for modeling a set of numbers, and as long as as long as they can be represented by those lines. And what if you have the case where the only number you have, or the only line you have, is this green line, right? It's all multiples of 3, and then you say remove multiples of 3. There's no lines left. So what does it mean to take the first term, or the second term, or term number 752? Like, it doesn't mean anything. And so I had to do something about that case. And the case, the choice was basically either, there's a notion called an option type, where you can say, instead of just returning a rake, so in the rake we have rake operations, we have rem is remove multiples, and I could have this, instead of returning a rake, it could return option rake, and that means that if it failed to find a if you remove the very last multiple, then or if you remove the very last sequence from the rake, then what you would get back none. So you would get back either some rake, the 2 constructors for option are sum and none. So you either get back none or you get back some rake. And I thought about that, and that's probably the way that the way you do it in functional programming, but the way I'm used, that's how I do things in Rust. But in MathLib, again, they do weird things with natural numbers, where rather than doing that for natural numbers and having subtraction, where if you say 10 minus 100, rather than saying, well, that's not a natural number, the result of that is negative 90, and you can't, that is not a natural number, so do we make subtraction return an option nat? No, you just make up a definition so that it says that 100 or 0, 10 minus 100 is 0. And likewise, 10 divided by 100 is 0, right? Because you can't have a 1/10, right? Because that's not a natural number, it's a rational number. So to get subtraction, you need the integers. To get division, you need the rational numbers. And then, I guess for trigonomic functions, you would need real numbers. And I guess for other things, you would need complex numbers. If you want to do a square root, you need complex numbers. But this is purely in the realm of natural numbers. And so I kind of took that idea and I came up with a zero rake. So I have it. I created a special value that it would return if you. That's just called the zero rake, and it is it has the slope of 0 and the constant term of 0. So it just produces an endless stream of zeros, no matter what you plug in. And you can also I don't know if this is useful or not, but you could use it to model a small set of numbers just by plugging in the exact constants that you want. And you could also, I was thinking about in the future, like using this, like the idea of this is it's a concrete model of a set that stores a small amount of information that it can use to generate numbers on the fly, right? So you can actually calculate those numbers, but you can also treat it mathematically and say it's just a set of numbers, right? And that's the idea. Well, actually, that's what a rake map is. Rake map is ties the rake and a set of numbers. But a rake map is like a concrete implementation of a set. A rake is a concrete implementation of a set, and a rake map is the proof that like what specific set it is and that kind of thing. And so this is the set of the number 0 repeated over and over again. This is the set of natural numbers. So you just 1n plus 0 is the set of natural numbers. 2n plus 0 would be the evens, and so on. Greater than 2 is this was a hack I did so that I didn't have to. Because prime numbers are all greater than 2, and some of the rules of divisibility that I want to use to define what is a prime or not apply to the number 1. So, I want to get rid of the number 1 and get rid of the number 0. And so that's what greater than or equal to 2. All right, so anyway, this 0 thing is what gets returned by the rake if you remove the last line. So if you have no lines at all, you get back just a constant zeros. And that means that you previously had nothing but multiples of 3 that are greater than or equal to 2, right? So it did not include the number 0, and then you removed all of those, and now you get nothing but zeros. Well, that's introducing a number, and so this theorem that I wanted to prove is false. And so what I did is I on the rake end of things, if you just call the rake and you say remove, the code says, find it, rem. So it says, if filter the list for all the things that are, so the number to remove is j, remove all multiples of j, partition based on j, so make j copies of the, j, turn each sequence into j sequences, and then filter out the ones that says, filter keeping the ones where the constant term is a multiple of, or is not, keeping the ones where the constant term is not divisible by j, so co-prime to j. And then if the result is 0, if the length of that list is 0, then we return this sequence, the 0 sequence. Otherwise, we create a new thing where, based on partition, you get a new delta, which is j times the old delta. and then you get the list, and then we have a proof that it's sorted, and kind of a redundant proof that it's that there's at least one, or I guess sorry, that the proof that it's sorted is actually the proof that it's not sorted. It's a statement that it's not sorted, so that we have to sort it later. That was another simplification I did, and then the rather than proving it's sorted, I just say it's not sorted, and then because I have to prove it everywhere, right? And then for h size, that's a proof that it actually contains a term. So here the proof is we just check, right? If the length is 0, then we have to return something that has a 0 term, it has a 0 sequence, and then if it is not 0, then we don't need a proof. We already checked, so the proof is that we checked. So on the inside, it just does that behavior, but from the point of view of the rake map, where we want to say that the set is preserved, so the set has a defining property, and what we want to do at every step is say that the new rake map that we return, so we start with a rake map that has some property, and then the new rake map has a new property, which is that the old property still holds, and as the numbers coming out of the thing. So it's a set of numbers that are there. So it's the same set, prop n is the same, but also, so it's filtered by the fact that that j does not divide any of the numbers that are left. So it's a filter, right? And in order to make this happen, like this is the type of the thing we're returning, right? This is a dependently typed language. So we start with a rake map that has any property whatsoever that we can build up, and we return a rake map that has the same property but with all of the multiples of n of j stripped out. That's the idea. And then to prove, right? So again, this is kind of what I was just talking about here. Is a proof that the rake contains at least one non-multiple of j. So I call it HNMR, HNM for H, kind of a pun because it has two variables n and m, but also it's the hypothesis that there's a non-multiple in R, right? So in the rake, and it just says that there exists an n and an m such that this j does not divide n, so that's, and that there's a number you can plug in, an m that you can put as input, so that you get the n out. Right, that's the idea. So there's an answer to this that exists, and it doesn't matter what it is, but it just exists somewhere. And that means that it will be, that this, whatever this term is, will be retained, and then that means that the resulting map is non-empty, and so it's not a 0. And then here's me, kind of stitching all this together. So we say the proof. This is the proof that it has this new property, right? And the proof is just based on those other three proofs. So we have rem drop, rem keep, and rem same. And then Aesop, the friendly neighborhood proof assistant, can just come in here and solve that for us. And then it turns out that inside of rem, we actually sort it, as I said, to put all the constants in order. And that is so that we can always find the minimum term by looking at term 0. In general, it's ascending up to the number of terms in the list of constants, but it's not ascending after that. Yeah. I mean, yeah, it's not strictly ascending. It kind of does a zigzag. And anyway, so then there's also a proof about sort, and then and so from those two proofs, we get the final proof that this holds. So this is kind of like a wrapper based on these three proofs that kind of puts it all together, and that way, from the siev's point of view, we can just call rem as long as we pass in this thing. And so anyway, that in the diagram, that is why rake sieve is not broken. because I have not provided that thing yet. So I have two things to do. I have a statement of this right now. I have a statement that when you do the partition step, the set is retained, or the numbers in the rake are retained, and I have but it's proved by the word sorry, so I have to fix that, and that's why it's kind of giving me a warning. It's yellow in here, so it's turning yellow here, and then this one is red because I've introduced this new constraint where the rake map, the thing that maps the rake to the set, contains a new requirement, which is that I provide this, the statement that there's that a non-multiple exists. That was, I think, yeah, has non-multiple rj. So the rake has a non-multiple j inside of it, and you have to pass that into each one of these proofs. Or I guess rather, rem drop and rem save. Rem keep does not actually need that because it's about keeping things that were already there, so we're not removing anything. Or it's not about that part of it. Anyway, that's the idea. Somehow rake, like you don't actually have to pass those parameters in. It's kind of a mess over here. But I thought I'd have to, they take like all these parameters. You need the following rake and whatnot. But if you don't pass them, then they're returned, right? So you can just pass in just enough to derive the rest of them, which is kind of neat. Because, again, there's no actual computation. It's just type checking. Okay. I mean, like at runtime, there's nothing is being done. It's all, this all goes away at runtime. It's just the compile step. Proof checking is type checking. Okay, so anyway, in the LeanSieve, where I'm using this rake map now, I have to pass in a proof that I have a number. So in the init step, there's two steps to find. There's init and next. So the init is where I initially set things up, and I start with the sequence. It's a little complicated, but the number is greater than or equal to 2. So I strip out the 0 and the 1, and then I remove the number 2, and I remove all multiples of the number 2. So I have to prove that 2 is greater than 0, so that's just by simplification. I guess because 0 is a multiple of everything, or everything is a multiple of 0 in this. I believe that's true. Eval 0 divides 5. False. Okay, so I guess it's not. I actually forget why I needed it. Oh, right. I actually don't know. Maybe I don't need that. But like it. That's interesting. It's possible I don't need this at all. That could actually just be left over from. I wonder if I take this out if anything breaks. Oh, maybe the partition step needs it. Oh, right, because you in order to get the new sequence, the way the partition step works is we multiply by that number. So if you multiply by 0, you would get 0 sequences, and so you would not be able to do it. So I have to have a positive number, right? Okay, so that's the reason for that constraint. So you have to prove that 2. That 2 is greater than this, and so you can do that by simplification. That 2 is greater than 0, which is obvious. I think you can probably say RFL here too. Okay. No. ACRFL? So ACR. Oh, no. There's a lag while it. Yeah, I don't know what it's called. So simp works. Simp. Maybe you have to say by RFL. Nope, that doesn't work. Okay. Anyway, simp does the job. Simp is just a simplification rule, and it figures out that something is greater than. Like knowing the goal, simp is able to figure out and the type checker knows what goes in this slot, which is a proof that whatever this number is greater than 2, is greater than 0. And then in this slot, we have to show that we have one of these terms. Well, so in the initial step, we have numbers greater than or equal to 2, and we're removing 2, so we have to show a number that is not divisible by 2. And so I say, well, just use 3. And then I have to prove that. So you know it's this has non-multiple, right? So it's so slow to jump to something. You click on something and it just doesn't take you there. But we're proving this statement. There exists some number n, so that's 3, that 2 is not divisible by n, or 2 does not divide 3, right? Okay. And then there exists some other number that you can plug into the rake to get the number 3 out. And for the list of numbers greater than or equal to 2, the first one is 2, the second one is 3, so you plug in the number 1. 0 you plug in to get 2, 1 you plug in to get 3. And so then the proof is, at this point, it should tell us that we have to prove that 2 does not divide 3, right? So first of all, we said we need to prove something. We have to prove that this thing exists. And so we say, okay, we use 3 for n. And we use, okay, now we have to prove that m exists. Right? And then we have to prove all the facts about m and n, which is that 2 does not divide 3. Well, simp already does that for me. But the hard part is this, right? I have to prove that the first term of this is 3, and so what it does is it basically does a compile time computation on it. So after I unfold these 3 things, and simp solves it for me. So it just takes the definition and just simplifies it and keeps applying simplification rules on the definition of the rake itself, right? This one, on which in turn triggers different, right? So that simplifies down to this: rake map greater than or equal to 2 simplifies to rake greater than or equal to 2, or, and then, well, that's just it's like a simple definition up here. That's just this line right here, with some extra stuff that is being generated on the fly. Proofs, all these proofs are being auto inferred or whatever. They're just they have default implications where or default implementations where the sorted flag is true, and then the proof of this is just by simplification. The proof of this is by simplification, and if it can't do that, then it'll complain, and then you have to fill in a proof yourself. But so that allows us to ignore half of this stuff and just write this, right? So they're default implementations and default proof. So that simplifies down to that, and now we've unpacked it to this, and then we have to figure out what rake term is. So if I remove the part about rake term, right, it's gonna, so we wind up with the actual rake. So here's that same, d equals 1, ks equals 2. So the list of constants is 2, so it's 1n plus 2. Those are the numbers greater than or equal to 2. And a bunch of proofs about that, and then term 1 equals 3. And the way to figure that out is to do a whole chain of simplifications, but I set some of those up as simplification rules by putting the word simp in front of them. So like for term, I didn't actually do it here. So I have to unfold term. That's the thing that I just deleted there. I have to unfold rake.term, And then once I do that, that boils down to something about arithmetic sequences. And in the arithmetic sequences file, is right up here, I stuck the word simp in there. So I used to have, I had several proofs where I was typing, simp, and then I would, or unfold or something. I would unfold asec, and then I would unfold term, and then I would unfold break.term, and finally I just realized I could just put the word simp, that I could just annotate these as being simplification rules, and the definition itself gets handled by simp. So there's some automation there. All right, so that means that all I have to do now is I say rake.term, and the simplifier is able to prove from all of that the number 3 is term number 1 in the sequence, and also that 3 does not divide 2, and therefore I have a multiple, or have a non-multiple of 3. All right, that the rate contains a non-multiple of 2. All right, so how did I do that? Well, I picked the next prime, right? Like the basic logic is I have a prime sieve, and I've scratched out some primes, and I want to scratch out the next prime. So hopefully, if I've done things right, there is another prime waiting for me, right? That's the whole point of a prime sieve, is that there's an infinite number of primes to be found, and you keep scratching them off, you keep finding more. So I've supplied this proof for the initial state, but what's causing it to break, what's all those red lines here, and causing, I mean, I just hand draw this diagram, but in theory, Lean could generate this for me. But the reason I have this marked red is because this is broken, and it's broken because I don't have that proof. Because like everything after here is upset, because RM is not a rake map. It is it's meant to be a rake map. It was a rake map, but then I added all these extra parameters. So I have to show that first I need to supply, so we can see what it's asking for, right? So C1, oh sorry, RM. But even that doesn't show up until you get to the next line, right? Just hit enter, and then on the what's happening here? But when I put my mouse over here, I can see what the type is. I'm expecting to see it over here, but it's just, I think it's not showing up because the next lines are broken. Right? I don't know. I have no idea why it's not showing up. I would expect it to show up here and then still give me an error about this. Oh, here. Okay, sorry. Here it is. This is the type of what it used to be a rake map, but now I've added some terms, and I had to make some of the terms explicit. And so, like, I don't know why you can't just, like, you can't, like, you have to supply both the thing and the, what am I trying to say? Like here, you have to supply both the J and the HJ, right? The proof. The J is a natural number, and this is a type. So this is a proof that 0 is less than J. The J is greater than 0. And likewise, all of these, because you repeat them so many times, you can just kind of like in that section, you can just put all your variables up here, and then you have to use them again. And this curly braces says that for this function, I can infer. All I have to do is pass in the proof that 0 is greater than J, and then it knows that I'm talking about J. I don't have to explicitly pass in the letter J. But for whatever reason, I couldn't extend that. I'm talking about the fact that this is a curly brace and this is a parentheses. If I make this into parentheses, it gets mad here. It gets mad here, and I have to fix that by typing in the letter J, by telling it explicitly what J is. But it should be able to infer that from HJ, and it can. So I do that. But for whatever reason, when you go to the next file, like another file over, it was unable to do that, and I don't know what that is. I don't know if that's just Lean, but it just says if you try and do that trick, it says it's unable to synthesize. So for all of these, you have to supply all these things explicitly. So you have to supply R prime, which is the rake, and you have to explicitly provide the proof that R prime is defined as the removal of J by passing. So like it allows the type to not contain the J, but it's still, you have to provide both of these, and I couldn't make that a default parameter. So I have to provide a proof here. By simp maybe might work. I don't know if it'll work or not. And I think I'm out of sync. I have to restart the file to update the imports. And it takes a couple seconds, and you'll see this yellow line. Oh, that's like the queue of lines that it hasn't processed yet. I'm going to close this so I have a little more room to work with. All right, so the simp was not able to do that, but what do we know about MP? MP is a prime, right? Oh, it's so HPGT give us, if we look at HPGT, we have prime greater than. So I think if I just put in HPGT, no. All right, so this is. I may have to say M dot. And I still have to provide that this number is greater than. Hang on. All right. Well, bottom line, I'm in the proving step now. So now I'm trying to fix this and fix this. So this might be a little tricky, but I think it's just a matter of declaring this as a simplification rule. The definition. You can see this little line going across the top. It's like really taking its time here. I got to find where min prime, or I'm not sure where I define this. Probably in prime gen, right? Or in prime sieve, right? No, prime gen. It should be. I don't know why it opens over here. Oh, this is the proof that it's prime. Okay, so I can have, so all primes are greater than 0. So so once I get it out of here, once I've converted it here, so I can say, I'm not getting a good feedback on here. Oh, I guess I am, because right. Okay, so by simp m.p, and I still have to prove that this is greater than C, but the way to prove that is to have that it's prime. So maybe I should say have. So we have nat prime m dot p, this number right here, and then you can say exact, and it'll find like a proof that it won't. Oh yeah, it can. Okay. I might not even need this, right? What's HC0? HC0 is that number is prime. Okay, so I don't even need this. This was the right, because the way the way this works is that LeanSieve actually provides the proof for you. All right, so you can see that's a parameter that you give it the initial state, and it and you tell it that you're a you prove to it that you have enough information. These two things that you have. So R is the set of things that you haven't scratched out yet in your sieve. So you have it. You have to prove that you are able to create a number C that is in that set, and that it's also the smallest in that set. And if you can do that, then the LeanSieve mechanism says, okay, for your data structure, you have correctly implemented the notion of a prime sieve, and so I can provide you with the proof that the number you gave to me is actually prime. So it's like that's the whole notion of this, is you have like a generic prime sieve theory, and then anything that implements the rules for that, which is basically providing those two. You have to provide you have to have a number that you know is prime. You have to provide a candidate number that you want to prove is prime. You want to you have a function that gives you the next prime, and then unfortunately there's some redundancy here, that there's a hypothesis about this, that all these things are I guess what this says is that the way next works is that it's a contract, right? This is a contract about how your implementation of the next function is going to work. It has to take the current state. It has to take the proof that the LeanSieve mechanism, like this file, is going to give you, right? Like, you've got two things. You have LeanSieve, and then you've got your implementation that has your data structures in it. And so you can make use of the general proof mechanism here. So what you do is you provide it with these four things. So the proof that you have a number, you have a prime that is the highest known prime that you have, or that that the sieve has generated. You have C, which is the number that you want to prove is prime, and then you have a function that takes a proof that it's prime, and a proof that you haven't skipped any primes, right? So this file gives you both of those things. This guy gives you both of those things to your implementation, and it does that from these two facts. So this is a hypothesis that you have to prove, that when you get these facts, you're able to produce the next, given, this says that if S prime is the next state after you feed in S and state S. Wow. You can say like this. I'll say like S dot next. I don't think I can say it though. Yeah. Okay. Well, it's conceptually that, and it has the proof that it's prime, that C is prime, and the proof that there's no skips. Then it produces a new P. Right, so this says this is your input, and then the output, right, is that or the implication or whatever, are these two facts, that the prime, the next prime in the prime of the next state is the C. So C becomes P basically. So that's trivial to prove. You just do an assignment and then show that you did it. And then this one is that the C for the next state is greater than the C for the previous state. oh, this is not sufficient. This is to make a prime sieve state, right? And then later on, you have to actually be a prime sieve, right? Like this is like the basics, right? And then a prime sieve uses this information, and you still have to provide two more things. Let's just say class prime sieve somewhere. Where is it? Well, I guess you prove you're a prime. I guess a prime sieve is a structure that contains that. So prime sieve driver is the thing I'm talking about. I guess I renamed it something. So in order to be a prime sieve driver, you have to first be a prime sieve state, which is everything I just said, and then you have to also produce these two proofs. So it's broken into two steps because like some of the mechanisms for this or that uses this depend like it just there's some back and forth, and so to break the dependencies, it's two separate things. But your implementation, like a rake sieve, is both a prime sieve and a prime sieve, or I guess it's a prime sieve driver and a prime sieve state. There you go. Okay. And what this is that R is some function up here that right, it's a set of natural numbers greater than or equal to 2. And that for all primes less than the number p, which is any natural number, doesn't have to be a prime, less than or equal to p, if q is a prime, so if q is any prime less than p, q does not divide the number in the set. Right? So in a sieve, these are all the numbers that have not been sifted out, right? The ones you haven't scratched out yet. The R is for residue remaining. It's been a while since I looked at this. I thought I was done when I proved all this stuff, and then it's like, oh wait. I mean, I know I wasn't done, but I thought I was like 90% done. Anyway, okay, so where am I at? Some of this is just to refresh my own memory, right? So I completed the proof, right? So I don't even need this, right? Because this gave me this. So all I have to do is just, I don't even have to say bye. I can just pass this in directly. So this is my proof that MP is greater than 0. And then what do I need for RM now? So I still don't have a rake map, right? I have what? Right, so if I like it, the red squiggly lines say I don't have a rake map, and it's because I don't have this proof that I have a prime. So now I need to say, and if I fix this, like all these things will go away. And I can, let's show that. So I need to show that well, I need to show that I don't have the that it does not contain a prime. Right, that it contains a number that is not divisible by c. Right, so it contains another prime or whatever. All right, so I'm gonna say HNMR, and let's say have. We have to call it HNMR. We don't have to call it that, but actually we can just say, we can just call it this. Then we don't have to give it a name. And so let's plug in the exact thing it's asking for. Well, we can plug in like this. Sorry. And then you can see that it inferred exactly what it needs to be. So I'm gonna explicitly put that type in here. Oh, I can't call it M. Interesting. I have to call it. That's why because m is the min prime, right? The min prime greater than that. That should be called. This should really be called like C prime or something. C prime. Do I have a C in scope? No, I don't. I just call it C. Whatever. C is the min prime greater. Okay. And then this is C def. All right, so this could really use some comments here. All right, so let's just comment this part at least. We have to prove to do the call rem. We have to show that it won't remove everything. So we must produce a proof that another prime besides C exists. It might make sense to move this into a new function or something like this. You might call it like something else. But for now, I'm just gonna, I can refactor later. This might be a general thing I want to put. It says I'm out of date again. I don't know what I changed, but let's start it. And we'll put the proof in right here. Actually, now it should work. Like all the lines should go away, except but they didn't. Okay, so we still have. We have to prove this, but let's see what else happened here. Or I just jump in and prove it. What's this red line? Probably because I just renamed that variable. I changed it from MP to C to that, right? Right. Okay, so if I prove, see, everything is now good. So I only have this yellow highlighted line here, which is this sorry. Right, so I guess next is the highlighted line. So next has the underscore because it depends on this. When I'm writing code, I try to keep everything on one like little section, like keep things like on one line or something, or not one line, but like a handful of lines. I don't like it when things scroll off the screen. It's the same here, but it's not quite so bad. Because in a way you're making an argument that has lots of little steps, and so like everything is kind of localized by itself. So I haven't found myself sticking to that rule quite as much about keeping things short. And in some ways it's like inevitable, right? Because like proofs are as long as they are. You can break them up though, and this might be a good candidate for breaking something up. But let's figure out what we need. All right, so let's just call this, what should we call it? We don't need to call it anything because we're only going to use it on the next line. It'll still be here, but in fact, we could put it in brackets, but I just wanted my own little, I just wanted a little space to work. Now we can use this. Now we can use this fact to remove multiples. Okay. All right, so as usual, over here it tells me what I need to prove. I am a little confused. Oh, I gotta say the word by here. Right, because if I say the word by, now when it regenerates after a second, it should change this. Yeah, there we go. That's what I expect. I should have to prove this statement. Okay, so how do we prove it? Well, we're going to introduce intro nm. Nope, cannot do that. We have to use something. Right. You intro, if it's for all, then you have to intro it so that you have an arbitrary one of the, for all n, you have to introduce n so that you have an arbitrary n to show that it works for any n. Like, you don't have any information, it's just some opaque variable n. This is an exists. So to prove an exists, we have to manufacture something where this is true. Or we can just prove it some other way. And I'm going to rewrite it. I'm going to do that by rewriting this as term it, using the function simp, the simplifier, and rewriting it as term, rewriting the rule term if, right? Right? What does it say now? Term if does not, because it's in a namespace. There's say rake term if and only if. And now we have to prove these facts. So we only have to produce an n now. We don't have to produce m anymore. Right? We had produced both of them before. Now we only have to line up here. Now we only have to produce an m such that that c does not divide that n, and that's not what I need. This is not. I may or may not need this. I need this fact right here. I need the other. I need. So let's say have rm prop, rm pred. Sorry. All right. So rm. What is rm? RM0 is a sieve. It should be called rake sieve 0. RS. You can't type that little lowercase s in, or lower. Okay. You can't type that little subscript 0 in this little box that pops up. Right, so rake sieve 0. Do I have an RM1? Because and here we have R. Okay, everything still checks out. Have I changed these files? Why is this one modified? Oh, because this is rake sieve. I don't think I've changed anything else. I just, yeah. So as long as all my file changes are in this, I'm good. Otherwise, I would check it into version control. Okay. You make too many changes and suddenly, you make one mistake and like cascades, and it's hard to find what the mistake was. Especially since there's such a lag between making a change and then going back. I like to make very small steps before I check into the version control. Like, I already proved this, and no lines are changed. This is all I did earlier was discuss. But over here, I've changed some stuff. I renamed a bunch of variables. Maybe I'll just go ahead and check this in. I'll wait. Okay, that's not actually it. What I want is the bijection, so hbij. Bij, I guess. Hbij. Hbij. It says for all n that if the property holds, then there is a term. So that allows us to acquire this term. So maybe what we do is we rewrite this. So we say simp with this. Rather than having it local, we just simp. Okay. So now it applied that rewrite. It applies this rewrite, and so now did that do anything? It did. But did it do what I want? All it did was simplify. So simp on its own did the same thing. Right? Simp on its own does the same thing. Right. So what I need to do is I need to rewrite, but pass it in the other direction, or simplify in the other direction. Not find instance of the pattern. Right there. Yeah. Maybe I have to use simp here. Yeah, this is what I wanted to see. So now instead of this, right, of having to prove something about a term, I only have to prove something about the property. So I just have to prove that there's a number with that property. Oh, I was freaking out for a second because, like, how do I know what the property is? It's an arbitrary property, but this is what the property is, right? So RSO. So HO is RSO prop. How often do I use this word? Because, like, that seems like it might be. I use it there, so. Okay. So I can simplify with. Let's pass this in there. So I have to tell it what H. You know, the problem with using these nice names is that you have to simplify them, right? Uh-oh. Maybe I just want HHO. Okay, so I gotta do this in a different step. First of all, I don't need this anymore. We just have to prove that there's a prop, but this fact right here is HH. Okay, so we say rewrite RSO shouldn't be hard. We just have to maybe I have to say rewrite HO HHO. I want it to take this and replace it with this with the word HO. Oh, I know what I say. We say subst HO, and that will rewrite all the rules like this. So we say substitute HO. Yes. Uh-oh. That didn't work. At HHO. Okay, it doesn't like at there. How about we say rewrite? Simp. Oh, I could say simp all here too. I bet if I do that, simp all might be better. Yeah, now all this stuff should be. Yeah, we have a little bit better. It got rid of all those HHO stuff. It expanded everything. So RSO prop is in here somewhere now. HHO, where did it go? Oh, it didn't. All right, so we have to say, yeah, I see. It didn't. It only changed HN. Okay, so we say I have to unpack this. So maybe I could either change this up here, but it's easier. Or I don't know if it's easier, but we'll just say rewrite. Say simp HO at HHO. And now we have this. Maybe what if we say simp? There we go. That's what I wanted to see. We needed simp all. So this can all be done one step. I've kind of stopped using some of these abbreviations for that reason. Because as soon as you introduce an abbreviation, you have to remove it in your proofs. All right, but anyway, all this whole line, what it did, you can see is it's changing this line right here, right? And if we look at it before and after, we just look at this bottom line with the turnstile. We go from a thing about C not dividing n, so exists n that C does not divide n, and there's some term, to that some n exists and it's a member of this set. So now if we simplify it, what R is, right? What it means is, right? What it means is that C does not divide n, and 2 is less than n, and q whatever. So I don't have to produce an actual number here. I can't produce an actual number here. Because I don't know what, this could happen at any point, right? I can't give it the number 7 because 7 might not fit this description. It fits it for step 1 and step 2 and step 3, and then that's it, right? So when I'm looking at 2 and 3 and 5, it works, but when I get to step 7, well, it no longer works because 7 divides 7. So this would not work. This would not be true. I have to have something that is not divisible by whatever number I'm looking at. So I think I have to have a prime that is greater than whatever prime I'm looking at. And I had to be able to prove that it was in the set, and that is modeled by this. But like all the other stuff that I've done up until now already proves this for me. Like in particular, this line right here says that the property RSO prop, R0 prop is called HO, or H0. And that says that if that property is true of a number n, then n is a number in this set. And it's a two-way thing. It's a if and only if, right? That means any number that this is already a proof that any number that is coprime and greater than the coprime to all the primes I've seen before and greater than the current prime, then that number is a candidate. All I have to do, and I don't have to produce a specific one, I just have to prove that one exists. And this line right here proves already for me that it's in the rake, it's in the set that I'm modeling. So all I have to do is just have any prime that's greater than that. If only there were a proof that there were an infinite number of primes. Well, there is, right? It's been known for many, many years. I think, who made that up? Euclid, maybe? And it's in MathLib. Or not who made it up, but who? I don't know. I think Euclid is the one who gets the credit for that, but for for a proof anyway. But this should just exist. This should just be in the I don't know if you can read that, but it says it's in MathLib data nat prime basic. So I think it should already be in scope, and all I have to do is say that that this is true. All I have to do is say obtain that there exists some, we'll call it P prime prime. We'll call it Q, whatever. I have a Q in scope. Q is usually my name for that. I'm already using N. Yeah, N is already being used. I try to use like Q for like query, the thing I'm looking for. C for candidate. I try to use like, even though it's I guess that's what mathematicians do in all their papers, and then I complain that their papers are unreadable because they use whatever. All right, so let's just find any Q greater than any prime greater than C. So we're going to obtain, and we got to call it Q. And we'll have a fact about it called HQ. And this is the type. sorry, this is Q, and then I screwed it up. And we need it to be bigger than C dot P. I wonder if it can just find it. I know what the name is, right? Yeah, and it should be infinite number of primes. It exists infinite primes, yeah. Boom. I think we can actually say RSOC. What we actually want is RSOC. RS0C. RS0.C. C. And we don't have to repeat it. We do. Maybe we do. Oh, it's a lowercase c in Civ land. And we don't have to repeat it. And then we can remove the by exact. Whenever you have by exact as your proof, you're just calculating something. There we go. And then we can say use Q. Now we have to prove all that stuff, but I think the proof is ESOP. Ah, come on, ESOP. Did it work? Almost. All right, we have to break it down. All right, so what do we have? We could say split. No, we have to say split. Oh, I guess split is for if then else. So this is looks like a bunch of ands put together. Let's do split ands. That should give us however many goals there are. 3 goals. And the first one should be pretty easy for ESOP. Such a lag here. Thing is a memory hog. Yeah, it's using like, oh, that's Chrome is using 3 gigabytes. I can shut down some Chrome tabs off screen here. This is proof that I was thinking about as an alternate way of doing this, rather than saying there are infinite number of primes. We could say that there are on any arithmetic sequence where you have the k term and the d term are co-prime to each other, that sequence will produce an infinite number of primes as well, which is what this paper is about. Dirichlet proved it in like the 1800s or something like that, when I don't know, somewhere around Riemann's time. But then Selberg in the I was just reading about this in this book. I've been reading this book called The Music of the Primes. You can't see it, but yeah, it's a book from 2003, and Selberg was still alive, and it has some quotes from him. Apparently, he and Erdős, Paul Erdős, collaborated, and apparently Selberg was a very like kind of solitary guy, and Paul Erdős is like, people talk about their Erdős number because he collaborated with so many people, and like super. You know, in the graph of mathematicians collaborating with each other, he's like one node that has like 5,000 lines coming out. Like he had like 5,000 collaborators. and he collaborated with Selberg, but they did not write a paper together because Selberg never would do that, and I guess they had kind of a falling out about it because they collaborated on a theorem, and then that went into this paper, but or rather that didn't go into this paper, that could have gone into this paper, but Selberg found another proof that didn't use Erdős's stuff, so there's a little drama about this. Anyway, I think it was this paper that they were talking about. But I actually found this paper earlier because he uses he apparently this uses the concept of a prime sieve on an arithmetic sequence, and so I was planning to, and it's an elementary proof, so it doesn't require complex analysis or anything. It doesn't I don't know, like Dirichlet was doing some kind of complex analysis, and this guy is doing it just like numbers, but it's apparently like it's kind of a tricky proof. Like it's got a lot of logarithms and calculations and stuff. So you can read up to 100 articles a month on it. Elementary proof of Dirichlet's theorem about primes in an arithmetic progression. Anyway, but I don't need that open anymore. I will keep this tab open. I'm just closing tabs to like to keep the lean chat open these days, even though I don't put it on camera. Notes about the script I'm writing. Need. Just trying to free up some RAM here. So 2 gigs of RAM for Hitchhiker's Guide to Logical. It's called Logical Verification. Is a book about Lean. Lean 4 using. It's all about like proving programs in Lean. I was trying to read it, and it's like I found it very confusing because they use like a bunch of stuff that doesn't come with Lean. I found it very confusing, and some of the even stuff that where they talk about it like it's out of date. This is the 2024 edition, but it's still just out of date. Some of these things don't, like the syntax doesn't work. So I found it confusing for that reason. Some of it does, some of it doesn't. Like this, see, but yeah, so they use a lot of terms provided by this Lovelib or whatever. All right, anyway, it's not useful. The midpoint circle algorithm. These are my tabs open. How am I doing? Hitchhiker's Guide. I went looking for that book, but I have it downloaded now. Lean for Web Server. This is what powers the live site. I kind of wanted to see. I kind of want to see how to talk to Lean itself. And this has nothing to do with anything. It just I thought it was an interesting algorithm, and so I thought I would about drawing circles. Okay, so have I freed up some memory? Oh, that video to watch later. Lean 4 video. Meta AI open. I was asking about the. I asked it to prove the Riemann hypothesis in Lean 4. It was unable to complete the task, but it did produce what looks to me like valid code. I don't know if these things actually exist or not. Try that later. Okay. All right, that's enough of that. Let's save. I guess YouTube is kind of a hog. The book was also talking about the partition function, which is something Ramanujan solved with. He's in this book as well, and talking about came up with an exact formula for this. Oh, actually, he came up with an approximate formula for this. You had to round up to the next number, and then it doesn't matter. I'm off topic. Yeah, I thought that might be another project that we need to do. I'm not going to worry about that right now. Speed. Important. And hopefully that will, although, yeah, okay, so now I've cut my memory usage in half. But still, still a gigabyte for Visual Studio Code because of Lean. And OBS is tearing up my server. Okay, back to this. Hopefully not so slow. Okay, so Aesop was not able to solve the problem. But why not? You would think he would know how to do that, right? If we should have this is prime somewhere, right? That's what this is. HC0. HC0 dot. All right, so I need to find something that more tabs open. Most of these are also about lean. All right, here's a. We need like prime def if. I probably need to have this back. So how do I have that follows from here? So have why is C0 font? 0 is not in my. Mm. Pressing Control, trying to undo that. Simp all. C0 is right here. Does it go away, or am I just not seeing it? Yeah, it goes away. Why does it go away? I don't want it to go away. I guess because it's redundant with this. Uh, so okay, so that's annoying. Also, we've got three let's fix that again. Yeah, sorry. Let's repair the file. Sorry. We had three proofs, right? Sorry. 3 goals, and so if we do them all, then that should, yeah, okay. So all the red lines are clear. Okay. So the first one, like that should follow from the definition of a prime. So so how about we break this into 2 things, and maybe if they're sometimes like Aesop doesn't dig into like ands, like it's a very simple pattern matcher. So you can see here it says left and right, so I can see what they are. So we'll say HQ less than and Q prime. We'll just call it Q prime. You know, the apostrophe is a prime. All right, so now I bet I think that this should follow from that, and I think if we say Aesop now, then Aesop can find unknown tactic. It's still slow. It says now very high, so it's doing something. It's still still can't do it. But it can't do it because it timed out. All right, so let's find the definition of a prime, which I believe is just called nat prime def. Well, if we have that they're not equal, okay, then this is sufficient. All right, so we have to prove that this number does not divide this number. We have that they're both prime, right? So we lost it that it's prime. So maybe that also could solve the problem. Have RS0 C have nat prime have Aesop should be able to find that. Nope. Sim. By sim. I should have said by Aesop. By Aesop. Come on, you can. There we go. Okay. Now. I have 2 numbers that are prime, and they're not the same. It should know this. So slow. What else can I kill? I was doing this whiz tree thing to free up some space on my hard drive. It's conceivable that it's doing a lot of swapping because, you know, like there's not enough space. %, but I think that's not my problem. Let me close some other programs here. Close this. All right, so let's try have. I want to eventually have it find this if it doesn't. Like I only have to prove that one of them is. Like, I don't even need this. We have that this is prime. We have that A is not equal to 1. Oh, I need to show that A is not equal to 1. But I can, okay, so have one again by Aesop. And then it should just find this. Exact should find this. And if not, we'll plug it in ourselves. Oh, but this is not exact. We have to simplify with this, or rewrite with this. Not prime p, and we have to tell it what we want. So q is prime, so we need to pass in hq prime. And we pass in this. We don't need the fact that C is also prime. Although ESOP might need it to deduce that. Okay. That did nothing? Oh, it's asking me for the proof that they're not the same. Right, because it needs to show that. Or maybe I need to rewrite it the other way. Oh, I see. This is my goal, and then okay, right. So the goal is that it doesn't divide, and then I can say that because one of them is prime and one of them is not 1, then I have to show that they're not equal rather than not divide. And so that should be simple because of this, right? So we can say simp. Maybe we can just say simp. Passing in this fact. And actually, this should be called q less than or equal to. You should be able to infer that they're not equal, right? Well, you can't. So, but we can say exact. There's some rule in here that says that a number that is less than or that maybe I can find it. It would be called like nat any of oh wait, is there less than or equal to? Surely that does not produce that. I put that in, right? Yeah, okay, so I had that number wrong. It should be less than, right? That's the whole point. And in fact, actually, Q is greater than. HQ greater than. There we go. And that was why it couldn't prove it, because I asked for less than or equal to, and so C could have been that. So, all right, so now I bet we have exact right here. Nope. Do this, and then try exact and see if it finds the... Oh, but we don't know what this is, right? All right, so we do need the fact that that's not 1, and then but ESOP is able to find. Oh wow. this is the proof that Aesop generated, but I think that's ugly. So either when that happens, I either just leave it as Aesop or Aesop, I don't know. Or we throw this into the list of things that we're simplifying on and see if it any of less. Okay, so that's what I want. At any of less. Say simple. It's right there. There we go. Ah, less than prime. That's probably the version that has the not equal rather than the, it has it as two symbols, I guess. Nat of LT prime. Oh no, the difference is it swapped the order of them. So A less than B says B not equal to A, but here I want it. Okay, interesting. Okay, so that's all right. So that proof is done. And probably say simp. All right, that's the proof one. Sometimes just for clarity, I like to show that I like to put in the like what I'm showing. So just say show and just copy and paste the thing, just to make it more readable when we when you're reading the code. Well, that's the proof. That's what that's what it's asking for. Oh no, that's not what it's asking for. To show that it's not divisible. That's like a little Unicode pipe character. Okay. No, still not doing it. What is happening? I wrote. I copied. Okay, I know what it is. I copied and pasted it at the wrong step, and it's already been transformed. All right, so we have to prove, show that C does not divide Q, and this is the proof. Right now, we have to show what? That 2 is less than or equal to Q. And this is exact. This is a property of primes. And here, I don't have a by clause, so I'm just inside of exact. So I'm already in the word by moves you from just applying functions, applying theorems as functions, to using tactics, and I'm already in tactic mode, so I can't get rid of this exact here. Okay, and then the last one. Actually, here I'm curious if I can get rid of. No. Yeah, this is just not a rule that you can sim. I'm just trying to find like a simple rule that simple. Oh, there we go. That's not going to work. Omega. Whatever. Omega is another little. Oh, actually, ASOP will tell me what it did. Ah, but this is why. Okay. Uh, interesting. See, to me, this follows from the fact that it's prime, and then primes are greater than or equal to 2. It's like this. And so if you had this in scope, but ESOP finds another path. All right, so anyway, we'll just let it be like that. The reason I do that, if you scratch this out, as long as every time you run this, the reason it's taking so long is because I have lines like this in it. Whereas if you have lines like this, where you're saying exact something, exact is a tactic that has to run. It's like a meta program, but tactics are meta programs. But this is a very simple one. And this is a very complicated one. So it does do some fair amount of caching, and that's why it uses up so much RAM. But it processes the whole file, and as the file gets longer, it tends to be slower. And this computer I'm on is not terribly fast. So that's why I'm trying to eliminate and use an exact proof if I can. Okay, so then we have to show this. So these little dots, the split ands split this term that we have to show. All of this is to show this, right? So we had to show that it's this, and then we had to show that that we have a term that exists, but then we replace that with the goal that, right, just to recap, we can rewrite this rule that there's a term based on the property of a rake, or rather the rake map. Let you rewrite it by saying that the property of this particular rake is that there's some n, but also that every n is a member of R, which is the numbers you haven't scratched out. The remaining numbers after you've done your sifting in your sieve. So it's a all right. So this is the last bit of that. This is why I don't call it Q. I knew I used Q for something else. Q is the other number. Okay, so let's rename Q to something. Like every one letter, I'm using it for something. Could just be N. Do we have an N? We have an N there. Whatever. The element cannot be renamed. What? We'll just call this Q prime. We'll change this from. We'll just call that HQ. This is a local variable within. All right. So for all, we have to show this. Show. And it takes a type, so our prop. This is what we have to show. We can rewrite it however we want, as long as it unifies with that statement. So we have to say for all Q prime less than or equal, so all natural numbers less than or equal to this, and then we can also call this C for simplification. Nope, cannot call it that. We have to do that. Okay. Oh, right, because C would be C is the candidate prime, and this has to be the prime that we know about. So for all q that are all prime numbers less than the current prime that we're looking at, the prime that we've just scratched off, not the candidate prime. So the high, yeah, right. We're always looking at a prime p that we've established as prime, and we've crossed it off the list already, and now we're finding the next prime. And basically, p is allowing us to define the set of primes less than, or the set of primes that we know about, and p is the greatest one, the biggest prime that we know about. So RakeSieve 0p, 0 is the RakeSieve 0 is the input, and then RakeSieve 1 would be the output. Right? That's what the 0 and 1 are. All right, so we have to show that for all q prime, it does not divide q. That is the property of being R. Okay, well, that should be pretty simple to prove because by definition, q is prime. Q prime is prime, right? Or rather, q is prime, and so okay, maybe it's not easy. All right, so we have to say that q we already know that q is greater than c, so we should be able to show that q is greater than this number. But we also have q is prime, so basically we have to say that q is not q prime, right? That's what I'm getting at. I have to show, if I can show that if I can show that have that q is greater than, strictly greater than this, then by omega. Can you do that? Yeah, okay. Oh, well, first we have to intro q prime. So now we have a q prime to work with. All right, so we probably can be able, if it knows that, it probably could find that q is greater than q prime by omega. Oh. So we need HQ prime. HQ prime would be the fact that Q, so this Q introduces a variable, and HQ prime will be this fact right here. So it should be, once we have that, we have Q prime and HQ prime. That should now Omega can find the information. In fact, probably we don't need this. All right, so then they're both prime, and or actually, let's do this. and then it should be the same proof. Oh, hang on. What do I have to prove? I just have to prove that they're. I have to prove nat prime. Well, I have this fact, right? So how do you do that? You say, oh no, you intro that fact. Oh, I see. So we have right. So we have q less than q or less than or equal to, and then hq prime. HQ prime less than or equal to, and HQ prime. I didn't want to spell it out, but whatever. Like some alien word. Hakola prime. And then now this should be that same. I bet it'll find that fact right here, or it'll find some other fact, but I think it should find this. No. Okay. You just say HQ prime. Is it because I put it? Watch, this works. Yeah. No. Maybe it's going the wrong. Maybe this is going the wrong direction. We have the facts, and we have that it divides, right? Which we have, but we have to do. We can't. It's not exact because of the not sign. We have to say simp. No. Okay, wait, this is giving an error. Did not find that's q prime. Oh, I have to show it the other direction. What am I doing wrong? Sorry, I want to see this on the screen, like where I can like read the thing. All right, so I need the proof that the thing on the right is prime. So q is prime. How do I know q is prime? Because of this. That's HQ. And then the equals needs to be this way around. Nope. I just leave this blank. Oh, so it wants it. I see. So if I provide, and then I say exact this. Oh, but if I say RWA, that should work. Rewrite and then use an assumption. So it should find this assumption right here. Oh, but we also have another goal here. Q prime is not equal to 1. That comes from the fact that Q prime, okay, so we have Q prime is not equal to 1 by ESOP. That's an exact. No, it's not. It's the same problem as up here. Oh, wait, hang on. Oh, so there is a thing. So that, if we have that Q is prime, or that C, okay, that C is prime, that should be it should be exact, right? H C 0. That should work. At prime RSS. Because this stupid thing removed it. Right. I don't know why, like, Omega is not for this, like, general proving stuff. ESOP is for this. Yeah, okay, that worked. All right, so now we should be able to prove, try this again. Simp all moves it. I don't know how to fix that. I don't know how to make simp not, not remove the thing I wanted to keep. Okay, so and in fact, now we can just plug this in here. We don't need, we can save a line here. Okay. Yeah, and again, so now that we don't need that, whenever you say by exact, that can just be reduced. And we still haven't proven the goal yet, but we're very close. Q is not equal to 1. Q prime is not equal to 1. That's right there. I'm going to say exact. And we had, okay, good. That's it. Kind of anticlimactic, but that's the proof. Okay, so this whole chunk now proves that that the prime sieve contains another number that is a prime, or the rake sieve contains another number. The rake contains another number that is a prime, and it meets all the conditions, so that now we can remove, you know, the. I think I closed my my diagram. Bring that one thing out. Was it cloud dot cloud.wolfram.com. Oh, wolframcloud.com. That's why I wasn't auto completing. Yeah, this has pretty good Chat GPT integration. You have to, as soon when you start chatting. I don't know Mathematica. We used it at work, last place I worked, but I didn't have a lot of experience with it, and I didn't. It's not open source, so I didn't really get into it that much. But I really do like their cloud thing. Maybe I'll play with it a little bit more now that I've. This is all free. I don't know how much usage you get out of it, but I didn't pay anything for this yet. All right, and since I don't know Mathematica, I use this little chat thing to have it tell me how to do things, and then I've been kind of tweaking their numbers. What was I going to say? Oh, right. Basically, so now I've proven that there's a number. You know, I've basically proven that it's safe to remove this line that has nothing but multiples of 3 because there are still other lines. That's the idea. And so that is the second to last. Or that was the second to last thing I needed to prove. So we see this now turns green, and so green, but there are no issues in it. There's one sorry left here. What's here? Oh, these MathLib doesn't want you to have anything with this in it, and I'm using MathLib, and so now it thinks I'm part of MathLib. I think that is something that MathLib should, like when you import, you turn that off. I guess if you import MathLib, it probably does turn it off, but I imported something in the middle of MathLib. Yeah. What am I doing? I'm going to check this in. So, all right, let's call it just to provide the proof that, let's see. So, LeanSieve, provide the proof that the rake provide. Actually, I gave it a nice name. Provide proof for the as non-multiple rather in next. And how about in LeanSieve? Commit and push. And if I haven't mentioned this before, that is this is at github.com tangent storm tree sieve, where sieve is spelled short with a short name. I'm probably going to change this to something else. Like this wasn't about a prime sieve originally. I was just going to model the rake thing, and use it for something completely different. But I got carried away. Anyway, all right. So that's that. That's where this is at. Okay, so guard has to have that. I found this, by the way. This is completely whatever, but this was a long time ago, but recursively f a function many times and collect the results. So if you don't want to collect the results, you can actually say something like, well, you can say, instead of this, you can say eval, and you can apply this function 10 times to the 0. Not fval. You just want the function. So there is an analog of J's power operator. N plus 1, and so it gives you the, call this an int. You say negative 15 int. You have to say int here? No. Okay, well, whatever. Yeah, I just didn't want, I wanted to make sure that it wasn't returning the 10, but we'll just do that. That should say 20 now. What? I think it's just screwed up now. Yeah, it's still showing that when I was talking about negative 15. Anyway, the point is that you can get this, but I don't know how to do the trace. I don't think you can do a trace. You can only do you can do the function power, but you can't. And you have this nice syntax for it, but you don't have the 20. That's what I expected. Okay. But yeah, you can only get the final result. You can't get the trace along the way. And in J, yeah, both options. All right. Anyway, unimportant. All right, that leaves me with this one thing. So it is now 2:40 in the morning. So I want to try this. I think if I try it, I'll be up till 6 in the morning. I'm gonna pass. I'm gonna call it. I'm gonna go to sleep, and tomorrow this will be the last one. So the answer was no. Sorry, it was not. How long is this video? It's only 2 hours. But this is now. Let's go to main and make sure that main works. And have I mentioned this is an incredibly slow algorithm? So watch what this does. So just finding the first prime numbers. Oh, it did. It found them. What if I do first 8 prime, or the first 8 prime numbers? See how long it's taking? It's not so much memory, though. I'm surprised at that. I thought this would be taking up a huge amount of memory. Taking up 30% of my CPU, but the memory's not growing that much. This memory's growing. That's interesting. But yeah, like this should take seconds. It should take a fraction of a second to do this, and it's not. I have no idea why this is so slow. Like it's a slow algorithm, but it shouldn't be this slow. That's my thought. It's trying to calculate this line here, right? Like it hasn't done this line. It's churning, trying to calculate the first 8 of them. It did 5, but 8 is too much for it. I guess I'll let it run for a few more seconds. I wasn't gonna, like, I didn't expect it to take quite this long. I knew if I did 10, it would take a really long time, but I didn't think it would take this long for just 8. Like, this is a trivial operation, right? It just should not take this long. But I have no intuition about like what Lean is doing right now. Like, it's possible it's running all these proofs on every step, like it's evaluating it as opposed to running it as a compiled function. Something changed here. I don't really know. I have no clue why it's why like if it's the simplifier working, like, you know, and it's just all happening in the compiler, then I could definitely see it being something along those lines. I haven't produced an executable. You can compile to an exe file. I haven't done that in a long time. So it's possible. Like, I don't see a LeanSieve for the compiler running. So it could be that Lean is just the you know, the interpreter. I don't know. Okay, well, this is taking forever. To be fair, this is not calculating just 8 primes. This is going to calculate 8 primorial. So we're going to have, how many terms are we going to have in here? It's a lot, but it's not so huge that it's inconceivable, right? Which is reflected by the fact that we don't have these natural numbers. So let's see, all the primes up to 8. So we're calculating a list that has this many. Oh, it is kind of long. So we have 500,000 at step 7, and we have 2, 3. We have 10 million at step 8. or step 7. Or if you count from 0. So this is step 0, has 2. Oh, and it's also doing a ton of string processing to print out the results. So it could just, maybe that's why maybe this is just buffering up the output to display over here once the message is done. That could very well be what it's doing. What if we just said, so R is a rake map. So how about we do R is a rake sieve. So rake map rake.ks.length. We just print it out and then restart this file. Wait. RM revert. Yeah, it caught me in the middle of something. What is R? Oh, we're also. Okay, so this algorithm is ridiculously slow. No, it's not. This is not a problem. We want SRM. This is not a problem. This only has 8 numbers in it. It only has the first 8 primes. Oh, so that means that, okay, I'm sorry. It's only printing out the list of numbers. So the real problem is that it's just allocating memory and space. So my thought was wrong. This is not the output. It's just slow. It's slow to allocate those 9 million items. What if we do 6? I think we can do 6. We'll set this line back to what it was. I would expect this to run fairly quickly because we only have to do 0, 1. I'm not sure if 6 is contained in here or not. 0, 1, 2, 3. We only do 6, right? That's 30,000 of them. That's the problem with this thing. It grows that quickly. And so the intent was to, yeah, so that evaluated fairly quickly. But it just slows down too much. I think the same algorithm in J would actually be a whole lot faster. Because J is good at allocating large numbers. And also I'm using a list here, and I could probably change, not here, but inside the sieve itself, I'm using a list, and I think I could probably change that to use an array, which is optimized. Okay, so anyway, but the point is that main worked. That as slow as it is, it does produce primes, even though I can only produce 5 of them, which is a whole lot of work, a month and a half of work to produce 5 primes, but that you could have done by hand in 2 minutes. This is my last statement. I'm going to call it, and yeah, I'm just kind of rambling now. So not quite the end, but I don't know if I'll do this next part on camera, but what I am going to do is a code review of all this stuff, mostly just to load it into my head again before of like everything in here, because once I prove this statement, I'll be working on the video for the Summer of Math exposition, and prove that these both are work. And so I'm going to be spending the next 2 or 3 weeks just like animating this stuff, and the hope is that I'll have a nice little video at somewhere before the end of August. Really, in the next 2 weeks. So I'm going to spend most of the next 2 weeks on this video. So I don't know if I'll have time to. I don't know if the timing is going to work out to prove this statement on camera. But at some point, I will do a code review. I might do 2 of them. I don't know, because I want the video to, to end with like, if you want to know more, there's like 900 hours of me struggling with Lean on here, and then there'll be a code review that kind of just walks through the code quickly, and also that will help me write the script. And I may also show this to some people. I mean, it's open source now, but I may ask some people on the Lean server to like chip in with suggestions or anything they see that could be improved about the style. Obviously, there's so many things that could be improved about the algorithm, but like once this is fixed, I do not expect this to be hard. But I'm just, if I start, it might take me 10 minutes because of all the stuff I've proven so far. Hope is that by applying this, like right here, like I only have to prove these two things, but I don't know what it is, and I don't want to dig too deeply into it right now. I will be up all night, and it's already 3 o'clock in the morning. But yeah, anyway, so stay tuned, and hopefully there'll be a video on my. Well, I'll do the code review on this channel, and then maybe I'll edit it. But very soon there will be finally a video after like 2 years on my main channel. I call this my secondary channel, but it's the only one that's been active for about 2 years since I made my last video. That's about to change. All right, thanks for watching, and see you again soon.